cardiac myocyte action potential and ECG correlation. This topic becomes easy once you stop memorizing numbers and instead follow one simple principle. The action potential explains the ECG. If you understand ion movement, you understand ECG waves. Let us build it step by step. What is the myocardial action potential? The myocardial action potential refers to the electrical changes across the membrane of cardiac muscle cells that allow them to depolarize, contract, repolarize, relax. This electrical cycle enables coordinated heartbeats. It occurs in all cardiac myocytes except the SA and AV nodal cells, which have a different type of action potential. The process depends on movement of three key ions: sodium, Na+, calcium, Ca2+, potassium, K+. If you remember the direction of each ion movement, everything else becomes logical. Two essential definitions. Depolarization means the cell becomes electrically active. Positive ions, such as sodium and calcium, move into the cell, making the inside less negative. This initiates contraction. Repolarization means the cell returns to its resting state. Potassium leaves the cell, making the inside negative again. This prepares the cell for the next beat. That is the entire electrical logic of the heart. Now we move to the phases. The 5 phases of the ventricular action potential.
We are discussing the ventricular myocyte action potential, which has 5 phases, numbered 0 to 4. If you look at the diagram, imagine the membrane potential tracing as a shape. It first moves sharply upward, then there is a small dip. After that, it remains flat for a short plateau. Then it slopes downward, and finally it returns to a flat resting level. So the sequence is a sharp rise, a slight drop, a flat plateau, a downward fall, and then a stable resting line. If you keep this simple shape in mind, rise, dip, plateau, fall, rest, the 5 phases become easy to remember.
Phase 0, rapid depolarization. This is the sharp vertical upstroke. What happens? Fast voltage-gated sodium channels open. There is rapid sodium influx into the cell. The membrane potential rises quickly. This phase corresponds to the beginning of ventricular depolarization. On ECG, this marks the start of the QRS complex, high-yield point. Fast sodium channels are responsible for phase 0 in ventricular muscle. Class 1 antiarrhythmic drugs act here. Phase 1, initial repolarization. Immediately after the upstroke, there is a small downward notch. Why? Sodium channels inactivate, transient potassium channels open, there is brief potassium efflux. This produces a slight initial repolarization. On ECG, this occurs during the early part of the QRS complex and is not seen as a separate wave. Phase 2, plateau phase. This is the most important phase for understanding contraction. Here is what happens. Voltage-gated L-type calcium channels open. Calcium enters the cell. At the same time, potassium leaves the cell. These two movements balance each other, producing a plateau. This calcium influx triggers calcium-induced calcium release from the sarcoplasmic reticulum. This leads to excitation-contraction coupling. This is when the ventricular myocyte actually contracts. On ECG, phase 2 corresponds to the ST segment. Critical concept: the ST segment represents the plateau phase during which mechanical contraction occurs. This is why ST elevation reflects myocardial injury affecting the plateau. Phase 3, rapid repolarization. Now the calcium channels close, delayed rectifier potassium channels open. Potassium leaves the cell in larger amounts. The membrane potential returns toward negative resting level. On ECG, this corresponds to the T wave, which represents ventricular repolarization. High-yield link: many long QT syndromes involve abnormalities in potassium channels during phase 3. Phase 4, resting membrane potential. Now the cell is stable again. High potassium permeability through potassium leak channels maintains the resting membrane potential at approximately -85 millivolts. No major ion shifts occur. On ECG, this corresponds to the baseline between beats. Phase 4 prepares the cell for the next depolarization. Now connect action potential to ECG components. This is where most candidates get confused. Let us make it simple. P wave represents atrial depolarization. It is independent of the ventricular action potential phases. PR interval represents conduction from the SA node to the AV node. It includes atrial depolarization and AV nodal delay. QRS complex represents ventricular depolarization, corresponds mainly to phase 0 and phase 1. ST segment represents the plateau phase, corresponds to phase 2. This is when contraction is occurring. T wave represents ventricular repolarization, corresponds to phase 3. QT interval represents the total duration of ventricular depolarization and repolarization. It includes phases 0 to 3. If you remember that QT equals the full ventricular electrical cycle, you will not confuse it.
Common examination misunderstandings occur at this point. Many candidates mix up atrial and ventricular electrical events. It is important to separate them clearly. The ventricular action potential explains the QRS complex, the ST segment, the T wave, and the QT interval. The P wave represents atrial depolarization and is not part of the ventricular action potential. Another common source of confusion is the plateau phase. During the plateau phase, calcium enters the ventricular cell. This calcium entry triggers contraction of the ventricular muscle. On the electrocardiogram, this period corresponds to the ST segment. So when you see the ST segment, think of active ventricular contraction occurring during the plateau phase.
MRCP key points and exam traps. Phase 0 is fast sodium influx. Phase 2 is calcium influx and corresponds to the ST segment. Phase 3 is potassium efflux and corresponds to the T wave. QT interval includes phases 0 to 3. Resting potential is maintained by potassium leak channels. Ventricular action potential does not apply to SA or AV nodal cells. ST elevation reflects abnormalities in the plateau phase.
Long QT syndromes often involve potassium channel dysfunction.